I found some slides from my friend Paul Geip, the author of our textbook, uh, Wind Power. And his photos here are the same ones that were used in the production of his textbook. So I'm going to quickly go through this PowerPoint and another file that he's made available for me to point out some of the things that maybe aren't as clear in the textbook. So what we see here, of course, is the difference between a horizontal axis wind turbine and a vertical axis wind turbine. We can see down here the size of the human beings that illustrate the size of these machines. So again, some of this is a review, so I won't be spending much time on many of these slides. So we have drag devices and lift devices. And of course, lift devices are the ones that are going to produce the most energy. These are some of the vertical wind axis turbines that the Darius design were known to be made for. And this is one that's known as a Panamoni. So this particular one is not that new. This has been around for quite a while, and I'm going to stop the video here and insert a clip of a different of a new take on this one that I personally witnessed several years ago when I was in Kansas City, Kansas, and so that'll be coming up here next. So the video that you just watched was shot by me in 2010. I happened to be in Kansas City for an occasion, and the hotel I was checking in, this was literally right next to my hotel. And so I went inside and I talked to the owner of the company, the Al Huber Corporation. And since then I've done some looking around and I've found that, yeah, the machine's still operating, but one of the problems is it's a 5 kilowatt machine. And a 5 kilowatt machine that costs over $200,000 is not very efficient, and it's not very cost effective. You can buy a much more energy efficient producing machine than you can with this. So you can see here on the screen here what the YouTube video is, and it's an 8-minute video. I'm not going to watch the whole thing, but the guys, they had their heart in the right place. But as it turned out, this company didn't last. So I'd suggest or recommend that you watch this video so you can learn a little bit about this new and improved stuff that just didn't pan out. Here's another site here. I did some searching for it, and I found this was the Newswire. This was in November of 2009, where they talked about the Windjet 5 turbine, right? And so it's a 5 kilowatt machine. All right, so this 5 kilowatt machine, here's the news release on it, and the telling sign was in the video where the CEO of the company from Korea stated that they didn't have any more chances to not succeed. So that was telling. So when we finally look over here at this press release down here at the bottom, it lists for more information. You can go to the aeswind.com. This is the Korean company that did this, and when you click on that, notice what happens. Safari cannot find that server. This company is no longer in business. So it failed. Now, I'm not glad that it failed, but it's just another example of how we can't try to, we can't. There have been many unsuccessful attempts to try to make what might look like new technology and new ideas work. And maybe somebody will find it, but for right now I wouldn't be investing in any of them until A, they're proven, and B, we can get some reputable data that we can look at and verify and compare to other technologies that are proven. And yet, here's another one that we found from the textbook. This Savonius here was actually put into use on several harbors lighting scenarios, so it made for a reasonable device to be used to provide the small amount of power that harbor lights need for the ships that are coming in and out of port. Again, some of these images are right out of the textbook. I'm going to just fly over them and make comments about those that are worthy of commenting. Pretty large machine here. What I like mostly about this is the quality of the photographs here. So we have a 4-bladed machine, and you can see that when it's not operating, the weight of those blades is going to significantly bear down on the bearing sitting at the bottom. Another one from the book, you can see the access ladder that would be used for doing maintenance. Note here the size of the individual working on this. So this is at the Ch6 pass. This was some actual testing that funds were spent on. There was grant money available to do testing on these, and the result was determined that they're not economically feasible. Yes, they produce some electricity, but by comparison to the horizontal axis machines, not as much. 2-bladed one with a traditional hot in the background. And again, yet another one. We saw this from the textbook. You can kind of get a date on it by looking at the old Datsun pickup truck here and the late 70s Ford pickup truck here. So the gyro mills, articulating straight angle vertical axis wind turbines. These have been around for quite a while, and yet we continue to see new iterations of them come up every year, and listed as the new and improved machine that's going to revolutionize wind turbine and wind generation. More of the same. Notice here we've got a little bit of a change here. We have angles. We have angles placed on the blades, and you feel free to stop this video and look at some of the details all you want. The ones with the X's through them are companies that are no longer in business. Different styles of blades. There's some great examples coming up here. So there's the single blader. As we read before, it didn't work out so well. Didn't work out so well, never made it successfully commercial. And there's our author, Paul Gipe, over there on the right. 2-bladed machines. Again, there are a couple manufacturers of these type left. By and large, there are some balance issues with them that have made them not as popular. Notice the one on the left has a blade that's one is shorter than the other, which would indicate that a failure was occurred. And this is a terrible sight to see, laying on the ground like this. This is all out in California, near Palm Springs, Palm Desert. I believe this is from overseas. There are many European companies that have this unique blade coloring requirements, theoretically for ease of aircraft visibility. So as we can see that there are quite a few here. Now I would like to mention that many of these photographs are dated. This is many of these photographs were taken 20 years ago, maybe 30 years ago. And so a lot of these companies are no longer available. One of the assignments you're going to have is to do some research on this type of thing and see what you can find is still available. By and large, the 3-bladed horizontal axis machines are the machines that are used in industry today. Look at those turbines all going there. That's an amazing sight. And it's a great place for it. It's in the middle of the desert. There's not a lot of activity. So, and by activity, I mean, human interaction. There's no golf courses, no shopping malls, no residential areas. So this is a great opportunity, a great location to put in a wind turbine farm. Okay, notice this slide here shows many more types of machines and manufacturers here. Here are the downwind machines, which we had talked about before. One of the things about the downwind machines is they somewhat have the ability to be passively yawed, which is a bit of an energy savings device. Notice what has happened here. Look how many less machines that there are. Okay. Again, blade materials here, we've got some cloth blades, some wood blades, some composite blades. By and large, we'll see composite blades. We can have multi-blades. These are the windmills or the pumpers, the water pumpers and grain grinders. The metal blades, of course. Fiberglass, well, you can see that as some issue. That looks like a fire occurred there. And again, here's some carbon fiber, and you can see the twist on some of these. They can be very sharp. And you can definitely see the twist, which is used for helping the blades, the turbine, to start its rotation. This is a photograph from the book, and from the textbook, it's very difficult to see the twist that's on here. But now that we're seeing an actual photograph of it instead of a small version in the textbook, we can see the twist on this is just significant. It's very dramatic. This is a blade color example you're not going to see many examples of, because with the black blade color, it tends to stick out very much. And for those that think it's aesthetically not pleasing to see them, they found that the white are much more easily blend in with the background environment. These turbulent strips were put here to take sound issues away, to try and reduce some of the whistling and the sound that these make. This is one that we saw before, the Vortec. The idea was that we could funnel some of the wind and pass it through here. It's actually a pretty large machine, and this particular design failed. Coning. Again, this is an example of how these are downwind machines. Okay, so the wind is going to blow from across the generator portion before it hits here, and it's got the ability to self-regulate by having this diameter get smaller as the wind blows stronger, and that's the coning effect. Now on to some of these vertical axis machines. One of the proponents of these, one of the main things that people like about these is they can capture wind from any direction. Well, this is true. This is true. We can't do that with a horizontal wind axis wind turbine. So several of the ways we're going to do this is with, I like some of these photos here. So here we're going to see someone actually using a hand crank and getting this Dutch windmill to face into the wind. I saw one just like this in Ireland 2 summers ago. It was pretty amazing. Here's a larger one. So something has to actively cause this thing to fly into the wind. I believe this is in Germany. Now here we've got a fan tail, right? And that's going to be used to get the turbine spun around in the correct direction, right? We're going to see that there's another version of this here. Again, old photos. You won't see many of these working anymore. They'll have all been replaced, long since been decommissioned. Most of the time we're going to use these yaw motors. I explained this before, and we can see up here on this fin are the anemometers and the wind vanes that are going to detect the speed and direction of the wind, so that we can get the rotor facing into the wind. Most of the smaller turbines that we're going to install are going to have tails, and those tails will be used to passively keep the rotor facing directly into the wind. And we'll see some more examples here in a moment. This is a strange type. You don't see many of these. So we have a 2-bladed turbine with an odd-looking tail vane, and an interesting shot here with the seaplane flying by. Again, here's more of these passive downwind machines. Enertech makes a machine that's very popular these days. We've got one down in Fort Atkinson at the high school. There's another one outside of Rio in Columbus, up in just north of Madison a little ways, another Enertech, so that's a very popular machine. One of the things about the types that furl is you don't have any controls, right? So we want to make sure that the turbine doesn't spin too quickly. So different methods of doing this. And in these examples, we're not using aerodynamic controls. We're actually using any types of furling, and furling is a term that's used to cause the rotor to be taken out of the wind, so it's no longer facing directly into the wind. We can slow the blades down with brakes or parachutes, or pitching blade tips, or finally spoilers. And overspeed controls also include ailerons and the ability to change the pitch or how the blades themselves are fixed to the rotor and whether or not they remain aerodynamic or not. So here are some of those controls. Again, this is a photograph right out of the textbook, and you can see not only a side view but also a tip view or a top view. If we were looking straight down from it, we can see how these brakes look when they're pushed out. Parachutes, that's interesting. I've never personally seen one of those. Notice what happens here on these tips. These tips can turn. That will certainly ruin the aerodynamics of the machine. All right. So these particular ones, they have mechanical brakes to slow it down here, this one here, and on this one here, this African wind power. These are designed, the blades are designed so that when they get spinning so fast, they just start to vibrate and flutter, ruining the aerodynamics of the blades, and so they're not able to keep up that speed. So they self-regulate their speed to protect the generator. This is a really interesting one here, using the vertical axis, right? And so as the wind blows higher and higher, there's a spring-loaded hinge right here, and that hinge is going to cause the rotor to tip and up and out of the wind. This is a side yawing so it's yawing to the right. So this blade is no longer facing directly into the wind because this tail has pulled it out of the wind. Interesting stuff here for the old windmills. More horizontal examples. Again, more examples that are unique and more antiques and historical pieces. So the conventional commercial turbines are normally going to use a variable pitch. Will cause the blades to actually turn. We can see that these blades, notice how they're not going to be capturing much wind energy, yet these blades are going to be able to grab the energy. Okay, this is a great example of pitched and not pitched, and these are all done electronically through the controls of the machine. This is one of the ways the tip brakes work. I think I've mentioned in the previous video that the Gaia, G-A-I-A, has this type of brakes, as does another one called Intertech, and there's one of those at Lakeshore Technical College up in Cleveland, Wisconsin, that's notorious for having those blade tips brakes deploy. More examples of tip brakes. This is an Intertech machine. I believe this is a E44. Okay, and so you can see those popped out. That'll certainly slow the machine down. Notice these machines are on the ground and out of service. Ailerons. Again, I'm not spending much time on these airfoils because these aren't things that are going to be, most of us will never see any of these other than in photograph. This is a picture from before, and here we have a Darius machine. That is a side view of a Vestas blade. I have something very similar here from a Berge machine, and it's you can see how it's made light and yet strong. And you can see the multi-layers that are put here to add strength and give us the correct pitch on this so that it will start and fly aerodynamically. That's right out of the book. This is yet another photo out of the book that we saw from Paul Gipe. And again, not worth looking at this much more. Something that didn't work out so well. There it sits on the ground. These should be removed. They're eyesores. They put a black eye on the industry. I like this photo here. We can see how the hubs are pitched. We can see how it will pivot through here. This isn't covered very well in the textbook, nor is this one. Each blade can be pitched independently. Not really a good idea when you think in terms of it for balance, but yet just another example of how manufacturers will try different things. These are the hubs on the ground. And again, this is a shot right out of the book. And where the gentleman is standing with his foot down here, that is the area where it would be connected to the rotor hub itself. Okay, this area here, with this hole we're looking in here, and to the two sides, those would be where the three blades bolt on, with a nose cone here on the front. So we can see that the hubs are fixed, but they're slightly adjustable. Look at the amount of adjustability we have there. They're not just straight bolt holes like we see here that connect the hub to the main shaft. These will pitch. We can see that these are separate from this outside, so there's the ability for this to spin around. Great shot there. Someone's got to put them together. That'd be you and me. So this is a traditional connection here, or where we can see the rotor is slid on. We can see the main shaft. That's there's another slide coming up that's going to give us a real example of just how big that is. We don't really understand how big these are until we get up close to them. We can see that the gearbox here is going to then speed up this blade speed so that the generator will spin at either 1800 or maybe as much as 3600 RPM. That's one of the requirements for a generator. They have to spin that fast to be synchronous. Again, this is an example of the same thing we saw before, right? So there's the hub. This is a great big pillow block bearing, the drive shaft, the gearbox. There will be a brake probably on the opposite side. There might even be a brake up here, but I can't tell from this photograph. And again, this top whole section is referred to as the nacelle, N-A-C-E-L-L-E. There's that big shaft that I'd mentioned, pretty large. Again, the asynchronous generators are going to generate voltage at the correct voltage and frequency. It's just that in lower winds, sometimes they may not be spinning fast enough. So this example here on the right, there's actually two generators here. This little teeny tiny one here, and then there's the larger one there on the other end. There's another good example coming up here. Gearboxes need to be rebuilt. There's a large industry partner in this over in Milwaukee that does a lot of gearboxes, and that's been a nice boost to the local economy to have all those wind turbine gearboxes be sent here for repairs. An old Enertech with exposed gearbox and generator here. Well, I think we saw photos of these before as well. Larger versions. Again, this has got the two different generators here. There's a pony generator and the main generator here. Clipper does something a little bit different. I suggest if you've got an interest in learning more about how these work, you check out Clipper Wind on the internet. Very interesting design here. It's made them a little bit unique. And we can see just how the gearboxes are going to work. This is a shot that we brought right out of the textbook. Notice a couple of these have been lined out. They haven't continued to stay in operation. The wind industry is very competitive. When the cost of solar electric went down so much, wind had no choice but to follow it in order to stay competitive. Wind has gone down by almost 80% in the last 10 years. I'm sorry, not wind, but solar electric has. And wind has gone down, not quite as well, but it's followed nicely. These are direct drive machines, right? So these, you can see those generations, those individual windings that we saw from the page before, right? So these are those individual windings, and there they are. Lagerway is going to have those right in place. Again, this is one of the ones that's from the Netherlands that is no longer being produced. But still, we can see just how it operated. Notice, no gearbox, right? It's direct drive, no gearbox. We put all those windings on the outside and come up with a great big direct drive generator. This permanent magnet one, this is very similar to what we have down in Fort Atkinson, the Northwind 100. If you take my climbing class here in the fall, I'll be glad to take you up and show you how this thing works. Generators themselves, we can see the various styles of these. We have a DC generator, an alternator, an induction or asynchronous generator. Then we're also going to have wound rotors and doubly fed induction generators, direct drive ring generators, which we saw an example of, and PMG, you might remember, permanent magnet, okay, generators, large and small. This is a great example of two different generators, small one, large one. When the wind is blowing fast and strong, the large one kicks in. The small one over here will be the one that's going to be running when the wind is at a low speed, so we can get some generation out of it. There's a Vestas over in Milwaukee that had one of these, and I believe they ran into problems with getting them both running at once. And can you see how they're connected together? Yeah, that's a drive belt. Looks really, it's probably a cogged drive belt. I can't see close enough here. I do know that the Vestas over in the port of Milwaukee, that one was, they disabled what they referred to as the pony generator. If you've had DCAC fundamentals or any of the motors and controls classes, you've learned a bit about generators and how they work. If you have more questions on this, it's a little outside the scope of this class, but I can connect you up with an excellent YouTube site that a friend of mine produces called the Big Bad Tech Channel. And boy, you can learn all you ever wanted to learn about electromechanical and hydraulic equipment right there. Again, we saw that slide before, and that one as well, and that one, and that one. The variable speed motors. Supposed to have better performance. Paul likes to say that no, not so much. The ability to correct the power factor, again, that might be a little beyond the scope of what we're talking about in this class. We can have a variable slip, okay, and so this is the ability of the rotor to actually track and keep up the speed with the varying rotating magnetic field. For the most part, we will have some slip so that the field might be working at 3,600 RPM, yet the motor rotor that's following along, the generator itself, it may be following at 6% less, so maybe 3,450.